Hi, my name is Kaitlyn Martin, and this is my semester project part 2. For my project 2 presentation, I'm focusing on the vertebrate nervous system and sensory organs, and how this system had time to change as vertebrates transitioned from living only in water to surviving on land. In part 1 of this project, I focused on early aquatic vertebrates, such as lamprey and bony fishes, and how sensory systems like the lateral line and visual pathways supported life in water. For this presentation, I will build on that foundation and follow the nervous system through key vertebrate groups, emphasizing how environmental change, especially the move onto land, shaped neural and sensory evolution. I will start with early fishes, including Porlepiforms, Osteolepiforms, and Elpistagids. These fishes still lived entirely in aquatic environments, but they showed early features that later become important for life on land. From a nervous system perspective, these animals already had increasingly regionalized brains, improved visual processing, and more refined mechanosensory systems. Their environments were often shallow, structurally complex, and variable in oxygen levels. This created strong selection for better sensory integration and motor control to navigate vegetation, detect prey, and avoid predators in cluttered habitats. These conditions helped drive improvements in visual processing and head-associated sensory integration long before vertebrates actually left the water. Tiktaalik represent an important transitional form between fish and early tetrapods. Although it still lived in water, Tiktaalik inhabited shallow, slow-moving environments where the water was often murky and oxygen levels were unstable. From a nervous system standpoint, the key shift here is not just limb structure, but sensory orientation. Tiktaalik had a more mobile head and reduced reliance on body-based sensory cues. This suggests increasing importance of head-centered sensory processing, especially vision and vestibular input. Being able to lift the head and orient it independently would have required more precise neural coordination between the visual system, neck musculature, and balance organs. This is an early step towards the sensory demands of life at the water-air interface. Ichthyostega and Acanthiostega represent early tetrapods that were still closely tied to aquatic environments. Their nervous system were adapting to a world that included both water and land. Sensory systems now had to function in two very different physical environments. Vision became more important for detecting objects and predators above the water's surface. At the same time, the lateral line system, which was essential in fully aquatic fishes, began to lose its dominance as reliance on airborne and surface-based cues increased. This transition required major changes in how sensory information was processed and integrated into the brain, especially for balance, orientation, and coordinated limb movement in shallow water and particularly terrestrial settings. Reptiliomorphs represent a lineage that was increasingly adapted to terrestrial locomotion. As animals spent more time out of water, the nervous system faced new challenges. Water provides buoyancy and constant sensory feedback through pressure and flow. On land, gravity becomes a dominant force. This created a strong selection for improved vestibular systems in the inner ear, better proprioception, and more precise motor control of limbs and the axial skeleton. Neural circuits had to support coordinated limb-based movement rather than body-driven swimming. This shift marks a major reorganization of motor control pathways in the spinal cord and brainstem. Amphibians represent an important stage in nervous system evolution during the transition to land. Their histories often include both aquatic and terrestrial stages. As a result, their nervous system must process sensory input in both environments. Vision becomes more specialized for detecting objects in air, while the lateral line system is reduced or lost in most adult forms. At the same time, auditory and vestibular systems become more important for spatial orientation and predator detection on land. This dual environment lifestyle places strong demands on sensory integration and behavioral flexibility. For my Module 3 organism, I chose the axolotl. Axolotls are amphibians that retain aquatic features throughout adulthood. One important nervous system adaptation in axolotls is the retention of sensory and neural characteristics associated with aquatic locomotion and perception, including mechosensory processing and aquatic-style motor coordination. Because axolotls remain in water, they continue to rely heavily on sensory systems adapted for detecting movement and vibrations in surrounding environments. Their nervous system supports precise control of swimming and feeding movements in low visibility habitats. Their life history shows how environmental stability in aquatic habitats can maintain ancestral neural traits even as other amphibians transition towards more terrestrial sensory strategies. This demonstrates that sensory nervous system evolution is strongly shaped by whether an animal remains aquatic or adopts more terrestrial lifestyle. Amniotes represent a major evolutionary step in the transition to land. With reproduction no longer tied to water, these animals became fully terrestrial. This greatly increased the importance of sensory system adapted for air rather than water. The lateral line system disappears, while vision, balance, and auditory processing become central components of environmental awareness. Neural circuits for posture and limb coordination become more complex to support sustained terrestrial locomotion. The brain increasingly integrates visual and vestibular information to maintain stability and accurately navigate three-dimensional terrestrial environments. Non-avian reptiles showed further specialization of the nervous system for fully terrestrial lifestyles. Reptiles rely heavily on visual cues and improved spatial processing to locate prey, detect predators, and navigate complex environments. The nervous system supports more refined motor control and behavioral flexibility, allowing reptiles to exploit diverse terrestrial environments. For my Module 4 organism, I chose the green anole lizard. Green anoles rely strongly on visual processing and spatial awareness to move through complex environments such as vegetation and tree branches. Their nervous system supports rapid visual detection of movement, precise limb coordination, and balance control while climbing. These neural adaptations are especially important because falling or misjudging distances in environments can be fatal. The select pressures driving these traits included predation, competition for perching sites, and the need to locate mates and prey in visually cluttered terrestrial habitats. This illustrates how reptiles evolved nervous systems specialized for visually guided behavior and fine-scale motor control. Across all these clades, the major driver of nervous system evolution during the transition to land was the dramatic change in sensory conditions. Water transmits pressure waves and electrical signals extremely well. Air does not. As a result, mechanosensory systems such as lateral line became less useful, while visual, vestibular, and proprioceptive systems became increasingly important. Gravity, uneven terrain, and the need for precise limb movement created strong selection for improved motor coordination and balance. These environmental changes explain why neural pathways associated with posture, limb control, and spatial orientation expand and become more integrated in terrestrial vertebrates. In summary, the evolution of vertebrate nervous systems during the transition to land reflects a shift from water-based sensory processing towards systems optimized for life in air. Beginning with early lobe-fin fishes, improvements in visual processing and head-centered sensory integration prepared vertebrates for life in shallow, complex habitats. Transitional forms show early reorganization of sensory and motor coordination. Early tetrapods and reptiliomorphs demonstrate increasing specialization for limb-based locomotion and balance. Amphibians illustrate how nervous systems can remain flexible across aquatic and terrestrial environments, while amniotes and reptiles show full commitment to terrestrial sensory strategies. Together, these changes show that transition to land required not only new body structures, but major reorganization of the nervous system to meet challenges of gravity, air-based perception, and complex terrestrial environments.